Oh, very good evening to all of you. So students, yesterday I have covered the PYQ of the engineering services for SOM, Stacy and Strain chapter, and today I am going to cover the questions of gates. So let us start one by one. This is a gate question of 2017 of 1 marks. An elastic bar of length L, uniform cross section area A, coefficient of thermal expansion alpha and Young modulus of elasticity is fixed at the two ends. So this is my bar. It is fixed at both the ends, and in this case the area of cross section is A, this is L, and coefficient of thermal expansion is alpha. Temperature of the bar is increased by T. So T is the temperature difference resulting in an axial stress sigma. So this is the thermal stress sigma. Keeping all the parameter unchanged, if the length of the bar is doubled, then axial stress would be, suppose if I increase the length and it is 2L, then what will be the change in the axial stress? So since the formula for thermal stress is alpha TE, this is the formula for thermal stress is alpha TE, means coefficient of thermal expansion alpha and T is the temperature, E is the Young modulus of elasticity. So it means length have no effect on the thermal stresses, whatever it may be, L or 2L or 3L. So if I increase the length, then it will have no change in the thermal stresses, because in this case change in length will be alpha TL. These are change in length, and original length is L. So change in length upon original length, this is strain. Strain upon stress is equal to E. So it means this thermal stress is equal to alpha TE. So it doesn't depend on the length of the bar. So my axial stress will remain the same. If it is sigma, then in this case also it will be sigma. So A is the correct answer. Number 2, consider the stepped bar. This is my stepped bar 1 and 2. This length is 400 mm, this is 900 mm, and its area of cross section is 100, and coefficient of thermal expansion is equal to 2 into 10 raised to the power 5 megapascal, means Newton per mm square. 1 megapascal is equal to this much. So there is the axial load of 1 kilonewton as shown in the figure. Segment A and 2 have cross sectional area of, its area is 100 mm square and this has 60 mm square. EO corresponding Young modulus of elasticity is E1 is equal to this and E2 is equal to this. Length is 400 and this is 900. Strain energy in Newton mm up to 1 decimal place in the bar due to the axial load is something which I have to determine. So what will be the strain energy, total strain energy of this straight bar? So what is the formula of strain energy? U is equal to, in case of axial load, the formula is P square L upon 2AE. In case of bending, it is M square ds upon 2EI. So this is in case of bending, and in a case of axial load, the formula is P square L upon 2AE. So in this case, total strain energy U will be equal to U1 plus U2. Strain energy of this portion plus strain energy of this portion. So U is equal to this U1 is equal to, my load will be constant. So this P is, since it is passing through the central axis, so this P will remain constant. So P means 1 into 10 raised to the power 3, this Newton, into L upon 2A. This will be sigma. So length in this case L1 is equal to 400 divided by A into E. This 2 will also be common, so I can take outside. So A1 into E1. A is 100 into Young modulus of elasticity 2 into 10 raised to the power 5 plus L2 900 upon 60 into 3 raised to the power 5. So simply I have to put in the formula. This is P square L upon 2AE. So in this case, P square is common. These 2 I can take common. So inside it will be L1 upon A1 E1 plus L2 upon A2 E2. So in this case, straightway by putting the value in the formula, I will get the total strain energy stored. So after getting the solution here, it will come to 35 Newton mm. So this I am not going to the detail calculation part, you can do. So finally the answer will be 35 Newton per mm. So I am going to the next question. So this is the question 1. In this case, a material under a state of plane strain, its size is 10 mm into 10 mm. So this is my square and centered at the point this. This is the point where it is centered. So after deformation, its shape is like this one. It is like this. If the shear strain gamma xy at this point is expressed as 0.001 K in radian, the value of K will be this one. So what will be the value of the K? My shear strain is equal to change in the angle. So originally my angle, this one was 90 degree, and after deformation, the angle is this much. This is 95 by 2 plus this much, this plus this one. Suppose this is alpha 1, this is alpha 2. So alpha 1 plus alpha 2, this is the total change in the shear strain. This and this is equal to this much. So whenever there is a change in the shear strain angle, so we take it as a negative. When there is a decrease in the angle like this, suppose there is a decrease in the angle, so we will say my shear strain is positive. And whenever there is an increase in the angle, suppose initially it was like this and finally it was like this, so there is a increase in the angle. So increase is something, we take it opposite. So this is minus. So it is minus 0.0005. This is the change in the angle. This is my shear strain, and this is equal to 0.001 K. So this K is equal to 0.0005 upon 0.001. So it will be this one. Since it is minus, so D is the correct answer. This is the change in the shear strain angle. Shear strain, this is phi xy. This is shear strain expressed in the change in the angle. This is shear strain. So this is basically phi x by 2 plus this is also phi x by 2. So my total change in the angle is this plus this. So this is the correct way of expressing this. Otherwise, for the purpose of analysis, we considered it on the one side, but actually it is like this one. So half is the change here, half is the change here. My change in the shear strain is like this, but only for the purpose of analysis we take it on the one side. So this plus this is the total change in the angle. So this is 90 degree plus this. This is nothing but this plus this. This is a shear strain. So shear strain he has given this much. So from this I can find the value of the K. So K will be minus pi upon 1 0 0 0 0 divided by 1 into 1 0 0 0. So this will be pi upon 10 means 0.50. So this is the correct answer. A 2 meter long actually loaded mild steel rod of 8 mm diameter exhibits the load displacement behavior as shown is figure. So this is the basic curve. This is a graph expressing my displacement on the one side and axial load on the y side. So this is a curve. So generally it is ideally plastic curve. So up to this yield point this is linear and thereon it is continuous. So lot of permanent displacement without increase in the load. So its plasticity is more. Anyway, this is not the point to discuss here. So simply he wants to know the assume the yield stress of steel as this much. So this is 250 MPa. The complementary strain energy in Newton mm stored in the bar up to its linear elastic behavior will be how much? So I have to know the complementary strain energy in Newton mm stored in the bar up to its linear elastic behavior. So linear elastic behavior is this one. So up to this, whatever will be, if I draw a line here and the area of this portion will give the strain energy source. So this is my load upon this load displacement curve will give the strain energy in Newton mm. So area of this much is, this is 1200, this is 1400, 12,000, 14,000. So this will be 13. So this is half. So it will be 12,500 kilonewton. So this is the load, and this is how much? So if I draw a line from here, then this will be, this is 2.5. So it is in midway. This is 2.5 in mm. So this is load, my displacement 2.5 mm. So the area of this will be this side multiplied by this side into 1 by 2. 1 by 2 into this much. So 1 by 2 into 12,500, this is in kilonewton. So if I multiply it by 10 raised to the power of 3, it will be in Newton into 2.5 mm. So this will give the value in Newton mm. So we can calculate it. So this will be, anyway, calculation part you can do it. So it will come out to 5625. This is in Newton mm. 15625 something Newton mm. So my complementary strain energy is this one. This is my complementary strain energy, and this is equal to the elastic energy. So this is my elastic curve. So up to this, if I remove the load gradually, so it will regain its original positions. My deformation will disappear. So this is the elastic energy curve, and this is equal to the complementary strain energy. So area of this portion is equal to area of this portion. So area of this is equal to this side plus into this side divided by 2, area of this triangle. A plate in equilibrium is subjected to uniform stresses along its edges. Its magnitude is this one, and so this is 30 megapascal, 30 Newton per mm square is acting in these directions, and in the y direction it is 50 Newton per mm square. The Young modulus of elasticity of the material is this one. Its Poisson ratio is this one. If sigma z is negligible, small, and assumed to be 0, then the strain, this is epsilon in zz direction, is equal to how much? So the formula is very simple. So strain in the z direction is equal to strain in xy directions upon E into m, and this will be opposite minus sigma yy upon me. Both have the different effect in this direction, and sigma zz upon E. So my strain in the z direction is strain due to sigma zz upon E and the reverse effect of the x and y direction stresses. So this will be opposite. So this, it means this will be minus. So here he has given the value of this one is negligible, small. So this I can treat it 0. It means this sigma xx minus sigma yy upon me, this will be my total strain. If I take this common, then it will be sigma xx plus sigma yy. So finally it will be minus 1 upon m is the Poisson ratio, and this is 0.3 divided by Young modulus of elasticity is this much into sigma xx plus sigma yy. So this will be this plus this. So both have the same nature, both are tensile. So this will be 50 plus 30. So it will be 80 minus 0.3 into 80 upon this is 11. So this will be the value. So it will be it will be 120 raised to power 12. I think some yes, yes, this is yes. So it will be minus number 1 and 120. So minus 120 means this is the correct answer. So there is no point of wasting the time. So minus 120 will be the right answer. So you can calculate it. 0.3 into 1t upon 2 into 10 raised to the power 11 Newton into mm 10 raised to the power 6. So it will be Yes. Mm, 120 into 10 raised to power, this is 6 and this will be 12. So one this minus this, it will be, so this is the correct answer. There is a rigid bar, rigid uniform weightless horizontal bar. This is the bar. This is the bar, is connected to three vertical members P, Q and R shown in the figure. Not drawn to the scale. All the three members so this is a horizontal bar. It is connected by three rods P, Q and R. There are three members. All the three members have identical axial stiffness, means A and E. This is the axial stiffness is identical. This one is constant. This A is constant and its value is 10 kilonewton per mm. So this is same for the three bars. Lower ends of bar P and Q, P and R rest on the this is a rigid horizontal surface while no load is applied. So this is the condition where no load has been applied. A gap of 2 mm exists here. So there is a gap of 2 mm under this load between the lower end of the bar Q and the rigid horizontal surface. When a vertical load W is placed on the horizontal bar, when you applied a load W in the downward directions, the bar still remains horizontal and this get displaced by 5 mm. So like this. Suppose these are, so this is the position. So this displacement is 5 mm. When you applied a load, initially when there is no load, this is the position, and after application of the load, it get displaced by 5 mm. So here this position will come here. So this difference is 5 mm. But this will be here. This gap of 2 mm will also be here. So this gap will still be maintained. Since this is a rigid horizontal surface, so after application of the load also its position will remain the same. So gap is 2 mm. This is 5 mm, this is 5 mm, and here the displacement will be 5 minus 2. So in the central bar the elongation is 3 mm, whereas in the outer bar the elongation is 5 mm. So there are two conditions in this case. One is condition of compatibility, other is condition of equilibrium. From these two conditions we can find the forces in the members. So this is my initial position, and after so this is the position here 5 mm. So this 2 mm gap will still be there. So it means extension here it will be 5 minus 2. In this case it is 3 mm, whereas in the outer bar this is 5 mm. So, and one other thing is that due to symmetry the force in the outer bar will be same. So this P is equal to R. Suppose force in this case is P. So in this case also it will be P. So if this is also P, and this force plus this force plus this force. Suppose this is in Q. So this P plus Q means 2P plus Q. This should be equal to this W. So this is my status equilibrium. Sigma V is equal to 0 means the force in this P and this P plus this Q is equal to W. So this is equation number 1. Second is this. If I take moment about this end, then this will be equal to if I take moment A, so it will be this P into so this distance is not given. Okay. So anyway, magnitude of the load W in kilonewton, round off to the nearest integer. Since this is centrally placed here, so if this is whatever difference symmetrical, if this is L, this will be L. So if I take moment about this one, so it will be P into 2L is equal to Q into L. So it means P is equal to Q by 2. So this is so this 2P plus Q is equal to W, or sigma V is equal to 0. This is the one equations, and in this case the axial deformation here will be force in this member P into length of this member L upon A into E. So this displacement PL upon AE is equal to 5 mm, and secondly this is equal to displacement in this case is 5 minus 2, so it is 3 mm in this case, and this 3 will be equal to force in this member, this is Q, into length of this member upon AE. So displacement in this case is PL upon AE, which is equal to 5 mm. Displacement in this case is equal to QL upon AE is equal to 3 mm. So 3 mm will be the displacement in this case. So if I divide it this by this, so it will, this and this will cancel each other, this and this also. So it will be P upon Q is equal to 5 by 3. So P is equal to 5 by 3 Q, and second, and this 2P plus Q is equal to W. This is one equation. Another, if I put the value of P in this case, so it will give 2 pi by 3 into Q plus Q is equal to W. So it will be 10 by 3. So Q into 10 by 3 plus 1 plus is equal to W. So this will be 13 by 3. So Q will be 3 by 13 W. So this is the value of Q. And what is the value of P? P is equal to 5 by 3 of this one. So 5 by 3 of this one is equal to 5 by 13. So this is value of P. This is value of Q. The magnitude of the load in, so W I have to calculate. So W is equal to, basically W is equal to this plus this. So 2P plus Q is the W. So total W is equal to 2 times of force in this member plus Q. So 2P means 2 into P, 5 by 3 W plus Q is equal to 13 by 3 W. So this will be So this will be the force. So, but I have to calculate in Newton. So I have to calculate in Newton. So this we can easily calculate, since value of P is equal to this one and Q is this one. So if I take moment about this sand, so this will be P into I think some mistake. Oh, this is not a question of I think we have wasted our time. Simply I have to calculate this one. AE is given. I simply have to put in the formula this PL upon AE is equal to 5. So PL upon AE is equal to 5. So P is equal to AE 5 into AE. So 5 into AE means this is 10 kilonewton. AE upon length. So he has oh yes, yes, yes. So this is yes. So this is axial stiffness, means 10 kilonewton per mm, means for 1 mm there is a load of 10 kilonewton. For 1 mm displacement there is a load of 10 kilonewton, and if there is a displacement of 5 mm here in this case, then it will be 50 kilonewton. So it means force in this will be 50 kilonewton, same force will be here, and in this case the displacement is 3 mm. So for 3 mm it will be 30 kilonewton. So it means my total force is equal to 50 plus 50 plus 30 is equal to 130 kilonewton. So this is a very simple questions. So mistakenly I have taken this as AE. So this is axial stiffness 10 kilonewton per mm, means for 1 mm displacement there is a force of 10 kilonewton, and my displacement in this case is 5 mm, in this case it is 5 mm, in this case it is 3 mm. So it will be 50 kilonewton plus 30 kilonewton. So total load will be 50 plus 50 plus 30, it will be 130 kilonewton. A prismatic linear elastic bar of length L, cross section area A, and made of a material which with Young modulus of E, axial tensile force is this one. When the bar is subjected to axial tensile force P1 plus P2, the strain energy stored in the bar are U1 and U2. If U is the strain energy stored in the same bar when subjected to an axial tensile force of P1 and P2, the correct relationship is what? Whether total strain energy is this minus this, or this plus this, or it is less than sum of this, or it is greater than sum of this. So it is very simple. Strain energy is equal to P1 square L upon 2A. In the first case, this is U1. In this case, it will be P2 L square upon 2A. And in the third case, when I have applied the sum of this is U. So U will be square of P1 plus P2 square into L upon 2A. So obviously, when you compare this plus this, then this plus this will become P1 plus P2 square upon into L upon 2A. But in this case, it will be P1 square plus P2 square plus 2P1 P2. So obviously, this will be more. So it will be P1 square plus P2 square plus 2P1 P2 upon 2AE into L. So this is more than this. What does it mean? My U is greater than the sum of this and this. So this is the right answer. So this is a case where square plate of P, Q and R of a linear elastic metal with side 1 meter. So this is 1 meter. This is my plate. This side, this is 1 meter from here to here, and it is also 1 meter. So this is my plate, and it is loaded in a state of plane stress. Plane stress means stress in the x and y plane. This is x and y plane. So this is my xy plane. So this is the xy plane. Under a given stress condition, the plate deforms to a new configurations. So after the deformation, this is it. This dotted line shows its new configurations. Under the given deformation, the edges of the plate remains straight. So this is after deformation, like this. These are also remain straight after the deformations. The horizontal displacement of the point 0.5 mm and 0.5 mm means a point having a coordinate of this one. So this is 1 meter, 1 meter. So coordinate of Q is equal to 1 meter, 1 meter, x and y, coordinate of Q, and coordinate of this point, this is 0.5 mm. So this is the coordinate of this point. What he wants to know, the horizontal displacement of this point in the plate OPQR, round off to 1 decimal place, is equal to what? So in case of when you take this 1 meter and 1 meter length, then the deformation is like this. And so if I plot it by in the first case, when the length is 1 meter, so it will be like this. In the bottom, there is a displacement of 20 mm this way, and on the top it is 10 mm like this. So this is when you take the whole length of 1 meter. So if I take half of this, suppose 0.5 meter, and this is also 0.5 meter, so this will be equal to like this. So this will also be proportionally half, 20, this will be 10, and this is 5. Okay. So this is 10 and this is 5. So the horizontal displacement of the point 0.5 meter in the plate OPQ in round off to 1 decimal place will be equal to, so here it will be, so this in this case it will be plus 5 in the center, and this will be half of this one. So half of this one will be this one. So it will be plus 2.5 mm. This will be the horizontal displacement in this case. Strain hardening of structural steel means strengthening steel member externally for reducing strain experiencing higher stress than yield stress with increased deformations. Strain occurring before plastic flow of steel material. Decrease in the stress experienced with increasing strain. What is strain hardening? First of all, you must be aware of strain hardening of the structure. There is a curve of stress strain in case of mild steel. It is like this. This is limit of proportionality yield point, and then it will be like this. This is my proportional limit. This is elastic limit. This is upper yield point, and this is lower yield point. So this is a case of permanent deformations with plastic deformation, you can say, without increasing the load. So this is my stress and this is the strain. So this point is the elastic zone, and from there on there will be a increase in the strain without further increase in the stress. But from here onwards, after this, there will be a change in the molecular crystalline structure of the material, and as a result of this, it will offer increased resistance in the force, in the stress, due to which further stress will be created, and this will be my ultimate point, and finally it will be the reposite point. So this portion is strain hardening zone. This is strain hardening zone. Strain hardening zone. So in this case, there is an increase in the stress with increase in the strain. So my strain is also increasing and stress is also increasing. So strengthening steel member externally for reducing strain experience. This is wrong. Second one, experiencing higher stress than yield stress. Obviously, here my stress is more than, in this zone my stress is more than yield stress. This is yield stress. And increased deformation. Yes, my deformation is also increasing. So this is the right answer. Strain occurring before plastic flow. Yes, no. Plastic flow has already been started. So this is wrong. Decrease in the stress. No decrease in the stress. It is increase in the stress. This is the right answer. Stress is acting on an Stress is acting on an infinitesimal soil element as shown in the figure, where sigma z is greater than sigma x. The major and minor principal stresses are sigma 1 and sigma 3 respectively. Considering the compressive stresses as positive, which one of the following experiences correctly represents the angle between the major principal stress and the horizontal plane? So this angle I have to find. Suppose if I draw a line higher like this and cut this element, so it will be like this. This is sigma z and this is tau zx. This is sigma x. This is tau zx. This angle is theta, and suppose this is the principal plane, and this stress is, suppose this is major principal. So this is sigma 1. Suppose this is my major principal stress. On major principal plane, my shear stress is obviously 0. Now if I resolve it, suppose this is A, B, C. So this angle, this is normal to this line, and this line is normal to this one. So if this is theta, this will also be theta. So for sigma v is equal, sigma h is equal to 0. Suppose I resolve along horizontally. So this will be sigma 1 into this length. This is AC. And suppose if I consider unit thickness in the normal to the paper. So this is AC into 1 will be the area. So this is my force which will act in these directions, and this force tau Zx is equal to, this is acting in the opposite direction, tau Zx into area of this will be AB into 1, its thickness, plus this is also acting in this direction. So this is sigma x into this side BC into its thickness 1. Now sigma 1 will be equal to tau Zx I think we have done some mistake. This will be tau 1 into, this will be sin theta, this will be sin theta. So its component will be sine of angle, sine of this theta. It will be sigma 1 sin theta is equal to tau Zx upon, if I divide it by AC, then tau Zx into AB upon AC plus sigma x BC upon AC. So this is sigma 1 sin theta is equal to tau Zx AB upon AC, this AB upon this AC. So AB upon AC is equal to cos theta plus sigma x, and this BC upon AC is equal to sin theta. So from this equation, what we can say, if I take this here, then it will be sigma 1 minus sigma x into sin theta. If I take on this side, it will be sigma 1 sin theta minus sigma x sin theta. Sin theta I have taken common. So sigma 1 minus sigma x will be this one. This is tau Zx into cos theta, and this sin theta, if I take it on this side, sin theta upon cos theta, this will be equal to tau Zx divided by this one, sigma 1 minus sigma x, and this is tangent theta is equal to tau Zx upon sigma 1 minus sigma x, and theta will be tan inverse into tau Zx upon sigma 1 minus sigma x. So this theta is nothing but the position of a principal plane with the horizontal. So this theta is the angle, this is theta p, position of the principal plane. This will be equal to tau Zx upon sigma 1 minus sigma x. So this one is the correct answer. For a linear elastic and isotropic material, the correct relationship among Young modulus of elasticity, Poisson ratio and shear modulus is this one. So this is very simple. This is very simple. E is equal to 2 into shear modulus G. In some books, it has been written as N or G, whatever you can see. So E is equal to 2G shear modulus into 1 plus mu, this. So this is the formula. So G will be equal to 1 upon 2 into 1 plus this one. So G is equal to E, this will be E. So E upon 1 plus mu. So this is the Right answer. And this is very simple question of 2 marks. So in this case, consider two linear elastic rod. This is HI and IJ. So this is HI and this is IJ. So there are two rods. So its area is 2A, its area is A. So both have varying sections. The rod are collinear. Collinear means the axis passing through this one and confined between two fixed plates H and J. Both the rods are initially stress free. The coefficient of thermal expansion is alpha for both the rods. Its coefficient of thermal expansion is alpha and alpha for both the. Temperature of the rod IJ is increased by delta 2. So delta T is the temperature we have increased. So delta T temperature, whereas the temperature of rod HI remains unchanged. Means there is no change in the temperature of this portion. Only change in the temperature of this portion. So this is the condition. An external horizontal force P is now applied at node at this one. You have applied a force here. It is given that A is equal to, this is basically alpha. The coefficient of thermal expansion is equal to 10 raised to the power minus 6 per centigrade, and this delta T is equal to 50 degree centigrade. This B is 2 meter. So this is also 2 meter. AE is equal to 10 raised to the power 6 Newton. This is A. Axial rigidity. Axial rigidity of the rod HI are 2AE and 2AE respectively. To make the axial force in rod HI equal to 0, the value of the external force is how much? So this is very simple. There are two rods of different cross section area, both are fixed. So there is a change in temperature, but this is fixed. There is no change in the temperature of this portion. Means whatever will be the thermal expansion, that will be only because of this portion. So this force P will be generated only because of the thermal expansion of this portion, because there is no force in this case, and moreover its temperature is also fixed. So this is basically useless. This part is useless. There is no change in the temperature as well as no contribution in the force. Means whatever will be the thermal stresses, that have to be done only because of this portion. So that will be equal to, force here is equal to this is P. So if I allow it to expand, this will be alpha TL. Alpha into, this is the temperature increase into its length. So this will be the thermal expansion. But this end is fixed. It means this P will have to compensate for this one. So it means this, if I thermal because of this force, what will be? This will be PL upon AE. So P into L upon AE, that will be equal to alpha TL. So this will be the formula. The displacement due to this force will be equal to the thermal expansion. There is no contribution of this portion. So LLN, this L is B in this case. So this will cancel each other. So this is, I am interested on this in this portion. So this is AE. So P force will be equal to AE, and AE is equal to 10 raised to power 6 Newton. AE into alpha. Alpha is this one. And temperature change in, this is 50 degree. So the L already cancelled. This is alpha into T into this one. So this and this will cancel each other. So P will be 50 kilonewton. So value of P is equal to 50 kilonewton. No. It will be Newton. Since this is Newton, so it will be 50 Newton. So this is very simple question, 1 marks. So this expansion has to be neutralized by this force only. So this is the next question. A hanger is made of 2 bars of different sizes. This is a hanger. There are 2 bars. Each bar has a square cross sections. The hanger is loaded by 3-point loads. 3-point load means one load is acting here and one load is there. So these are the 3 points where the load is acting. In the mid vertical as shown in the figure, ignore the self weight of the hanger. What is the maximum tensile stress in Newton mm square anywhere in the hanger without considering stress concentration effects? So maximum tensile stress, where the maximum tensile stress occur in this portion, whether in this portion or these portions. One thing is very clear, my load is passing through here. So if I draw a free body diagram, then this will be like this one. This is for lower portion, this is 50 kilonewton. So this will be 50 kilonewton. So this is the free body diagram of this one. Now for this portion, if I cut it in this portion, so this will be like this. If I see from here, total load acting in this direction is equal to 50 plus 100 plus 100. 100 plus 100, all three have the same directions. This will be 100, 100 and 250. So it will be 250. This is the principle of superposition. So this is 250 kilonewton. So stress in this portion will be equal to load upon area. 250 into 10 raised to the power 3 is in Newton divided by its area. This is square cross sections. So this will be 100 into 100. So this will be stress in part 1 and stress in this part will be, this is 50 is in Newton divided by area. This area will be 50 into 50. So this will be, this is 50 into 50 square cross sections. So this and this will cancel each other. This is 1000 means it will be 20 Newton per mm square in this case. And what about in this case? So this is 25. So this is 20 and this is 25. It means in this portion the stress will be more and the amount is this one. This is 25 Newton per mm square. A 2D thick plate with modulus of elasticity E is this one and Poisson ratio is mu is in a plane strain condition. This displacement field in the plate is given by U is equal to, this is xy plane and this is a curve. So it is equation is U is equal to cx square to y, where U and V are the displacement in meter along the x and y directions and c is a constant. Its value is in this way. The distance x and y along x and y direction respectively are in meter. The stress in the x direction sigma x axis is equal to this much 40x y Newton per meter square and the shear stress, this is tau xy is equal to alpha x square. What is the value of the alpha in this case? So this is a slightly tricky question, but anyway, So first of all, my strain in the xy direction, what is the formula of strain in the xy direction, x direction? So this is sigma xxx upon E minus sigma yy upon me, and sigma y is equal to strain in the y direction will be sigma yy upon E minus sigma xx upon me. This is the formula. So if I want to know the stress sigma x-axis, then I have to multiply it by 1 upon m. So if I multiply it by 1 upon m, so this will be square and this will be this one. If I add this and this, so this and this will cancel each other. So I will get 1 upon m. 1 upon m is basically mu. So you can write mu epsilon x plus mu y is equal to this plus this. So this will be sigma. I think I've done some mistake. So I have to eliminate sigma yy basically. So I want to know this value. So for finding this value, I have to eliminate this one. So for eliminating this, I have to multiply by this one. So this will be this, and this is this one. So this will be epsilon x plus 1 upon m, or mu you can say, into epsilon y is equal to this plus this. So this plus this will be sigma xx upon E into 1 minus mu square. So this sigma xx will be E into epsilon x plus mu into epsilon y divided by 1 minus mu square. So this formula I will get. I will get this one. This is sigma xx is equal to E into epsilon x plus mu into Ey y upon 1 minus mu square, and this will be equal to, so with this I will get, so this is the formula for this one, and this is mu is equal to u is equal to cxy into y in v is equal to 0. This applies x strain in the x direction will be delta u upon delta x plus mu into epsilon y in the y direction will be delta v upon delta y. So it will be equal to E upon 1 minus mu square. This mu upon x will be this one. If I take partial derivative of this one, so this will be 2cxy. 2cxy. This I will get plus this is constant, so its partial derivative will be 0. So I will get this one. I will get this one. So sigma x is equal to this one. So this is the value of sigma x is equal to E upon mu 1 upon minus mu square into 2cxy plus 0. So this is this value, and when x is equal to so this value has been given by as a, so this is 40xy. 40xy. This value is equal to, this is 40xy is equal to this much. To cxy is equal to this one. It means 2cxy is equal to this one. And what is the value of E? The value of E is equal to 1 and 1 minus mu square. 1 minus mu square means 1 minus 0.5 square into 2c. So from here we can calculate the value of the c, coefficient of c. So this c will come out to, after this solving it will come 15. So this will be 15. So coefficient value c is equal to 15 and sigma x is equal to 40xy Newton per mm square. So this is the value of c. Now shear stress is equal to tau xy is equal to alpha x square. So this is alpha x square, and shear strain pi xy is equal to, what is this? this is equal to displacement in y with respect to y and displacement in the v direction with respect to x. So this is this one. So with this you will get shear strain. This is a xy plane, and the value of u is equal to this much. So its derivative will be with respect to y, it will be cx square with respect to this one, and derivative of this will be 0. So it means phi xy is equal to cx square. Phi xy is equal to cx square, and what is the value of c? It is 15x square. So 15x square is my shear strain. Shear strain is equal to 15x square. And what is the value of shear stress? Tau xy is equal to, this is alpha x square. So tau xy is alpha x square. And shear stress upon shear strain, tau xy, this is the shear stress upon shear strain, phi xy, this is nothing but modulus of rigidity. This will give n. Modulus of rigidity is shear stress upon shear strain, means alpha x square upon 15x square. So this will give modulus of rigidity n, and this n is equal to, so n is equal to this is alpha upon 15 n, and what is n? N is equal to E upon 1 plus E is equal to 2n into 1 plus mu. So n will be 1 E upon 2 into 1 plus mu, and this will be E upon 1 plus mu into 2. So with this it will become alpha upon 15 is equal to E. What is the value of E? This one, upon 2 and 1 plus mu, means 1 plus this means 1.5. So this will become 3 into 5. 5 into 1 is alpha is equal to 5. So this is the right answer. So it is 5 Newton per raised to the power of 4 Newton divided by m4. So this is the value of alpha. So slightly a tricky question. So this is the next question. There is a 3 meter long horizontal rigid uniform beam. PQ has negligible mass. The beam is subjected to a load of 3 kN here. This is a concentrated load here, vertically downward force at 1 meter from P. This is P as shown in the figure. The beam is resting on 2 linear springs. So this is Kp and this is Kq. At the ends P and Q. For the spring at the end, the spring constant are Kp. So this is 100 kilonewton per meter. This is stiffness Kp. For the spring at the end P, this is the one. If the beam does not rotate, under the application of the force and displaces only vertically, the value of the spring constant Kq, how much it will be? So does not rotate means it will remain horizontal. Had it been rotated, so it will be like this. So there is no rotation, it will be like this. So I have to know the value of Kq. This is a 1 mark questions. So we can find it. First of all, I have to find the forces here. So this is, you can treat it as simply supported beam. So this is 3 kilonewton, this is 1 meter, this is 2 meter. So obviously force in this way will be 3 into 2 by 3. So this will be 2 kilonewton reaction here, and this is 1 kilonewton. So this is 2 kilonewton and this is 1 kilonewton. So 2 kilonewton means this is my force here. So force, this force divided by its displacement will give spring constant 100. So force 2 kilonewton divided by its displacement or deflection, whatever you can say, this will give you, this is spring constant, this is 100. So delta is equal to 100 by 2. No, delta will be 2 by 100. So it will be 2 by 100. So delta is equal to 2 by 100, and delta, this delta will be same here. So in this case delta will be Kn. This is 1 kilonewton divided by this 1 kilonewton is the load divided by its deflection. Deflection is 100 by 2. So this is the deflection delta. Oh sorry, this is 2 by 100. So if I put the value of 2 by 100 here, so this display load is this one, I will get 1 into 100 by 2 means 50. So 50 is the its spring constant, its stiffness, spring stiffness is 50. So this is the right answer. Secondly, consider a rigid bar ABC supported by 3 pin jointed links BD, and this is CE, subjected to a load P. Load is acting here at the end as shown in the figure. The axial rigidity of BD and CE are this one and this one. Axial rigidity means value of AE. Value of AE for this portion or this BD. So this AE for BD portion is equal to this much kilonewton, and for this AE for CE portion is equal to 15,000 kilonewton. If CE elongates by 5 mm, what will happen? When you applied a load, so this, there will be deflection like this, and this will behave like a cantilever. So obviously there is some deflection here. So what he says, so there will be tensile force in this CE portion. So deflection in this case is 5 mm here due to the load P. The magnitude of the downward deflection in mm at the end A would be how much? This I have to find out. So this is a rigid horizontal bar. So obviously it will bend like this in a straight way. This is 5 mm and this I have to know. So it is very simple. This elongation is 5 mm. So elongation in this case it will be PL upon AE. Formula is very simple. Force in this member divided by, so this is P and this is, so first of all I have to take the moments also. So this, suppose force in this case is, this is, suppose this is F. So if I take moment about this, so this will be P into 400, this will be anticlockwise, and this will be balanced by the force because of this one. So the force is F into this length is 200. So this is half of this one. It means This is 2p. So if this is p, this is 2p. Force in this will be 2p, and total upward force is 2p. It means downward force will also be p. So this, if this is pp, so there will be a reaction of p also. This p plus p should be equal to upward force p. So force I have calculated. So this is p, 2p and this p. Now this elongation is 5 mm. So force in this, what is the value of force is p? Force is p. And length is 300 PL upon AE. AE is equal to how much? It is 50,000 kilonewton. So this is 15,000 kilonewton. Means 10 raised to the power 3, it is in Newton. So it will be, this is in mm and this is in Newton. And this deflection is equal to 5 mm. So from here we can find the value of the P. In this equation we can find the value of the P, and P will be equal to this will be, this is 15,000 kilonewton means is P into length. If I this pi into 5, 25 into 10 raised to the power 3 into 10 into, this is in Newton. So we can say this is 250 kilonewton. So my P is 250, this P is 250 kilonewton. P is equal to 250 kilonewton force here, and if this is 250, so obviously it is 2p, so it will be 500 kilo. So force in this, so this will obviously 500, it is 2 times of, so this is 500 kilonewton, this is 250 kilonewton, and this is also P, so it will be 250 kilonewton. Now how much will be the deflection here? So this deflection is equal to force in this rod, this is 500 kilonewton into its length, this is 200, divided by its AE. AE of this portion is how much? This is 22,500. So this will come out to be so this will be 40 by 9. So 40 by 9 means 4 point something mm will be the deflection here. Means the deflection here is 5 mm and deflection here is, this is 40 upon 9 mm. So I can find the deflection here. So first of all I have to find value of this much. This will be equal to, if suppose this is x from here, so this is total is 200, so it will be 200 minus x. So this 40 upon 9 divided by this length is equal to, this is 5 mm on this length. So with this we can calculate the value of the x. So from here we can find the value of the x, and once the value of x is known, I can put the value of x here. So this is known, this is 200, so this length is 200 plus x, this is the total length here. This already I know, so this is known, and this is also known, this I have to find out. So these are two triangles, one is this and another is this being triangle. So this delta upon this is 200 upon x plus x, this will be equal to this 40 upon 9 divided by this x. So this x already I have calculated. So after putting the value of x in this equation, I will get this delta, and this delta will be approximately 13.88, you can say near about 14 mm. So calculation part people can do. The next question is, the homogeneous linear elastic rod AB is connected to a linear elastic spring of this one BC in between the fixed support A and C as shown in the figure. The cross section area or modulus of elasticity and coefficient of thermal expansion are this one, means its area is 500 mm square, and E is equal to 60 into this megapascal, means Newton per mm square, and alpha is 12 into 10 raised to the power minus 6 per centigrade. So these are the value here is given. The stiffness K of the spring BC is this stiffness, this spring stiffness here is given this much. Now the internal force in kilonewton that will be developed in the spring BC when the temperature of the rod AB is increased by 100 mm. So what will happen when I increase the temperature? So obviously there will be some expansion. So this is delta, and delta is equal to alpha TL. Thermal expansion is equal to alpha TL, and this expansion will have to be neutralized by this spring. So obviously this is a spring, so obviously this will provide some kind of yielding. So some yielding is there, straightway it will not applied a force, reactive force will not be there, there is some amount of yielding. So that yielding will be, so this, if this is the thermal expansion alpha TL, and due to its stiffness it will offer some amount of yielding. So means my final elongation will be alpha TL minus yielding because of this one. And how much will be the yielding? How much will be the yielding? Suppose force developed here is in P. So for 1 mm or for this, for 2500 Newton, so there is a deflection of 1 mm. Suppose if my force is P, then how much it will be? 1 upon 250 00 into P. So this will be the yielding, this will be the some kind of flexibility. So this will be P upon 250. So this much will be the flexibility of this spring. So my total expansion, and this minus this will have to be resisted by the thermal forces developed here. Since both the ends are fixed, means my final deflection will be equal to 0. So whatever will be the net deflection, that have to be neutralized by the thermal force. So what will be the value of that thermal force? This will be equal to PL upon AE. So if force is P and displacement will be PL upon AE. So this is the basic equation. From this you can find the value of the P. So suppose by putting the value here, alpha T is a how much? Alpha 12 into 10 raised to power minus 6, and temperature is 100 and length is 3. this is 3 into 10 raised to power 3. So this is my alpha TL, this one, minus this will be the yielding flexibility which this spring will offer. This will be P upon 250. This is in mm. Suppose this is my thermal expansion is 25 mm, suppose, and this spring will provide some flexibility. Suppose this is 5 mm. So this will be 25 mm. So for this 25 mm, my thermal force will be required because this has been neutralized. So this minus this is equal to, this is PL. What is the value of L? This is 3 meter, means this is length upon AE. And what is the value of AE is equal to this much. Value of the yes, this is AE. So AE is equal to 500 area into E. So if I take P, so this I will consider, this will be 1 upon 250 plus this much upon 500 into 60 into 10 raised to power minus 3. This I will take common. So this, if I take on the left hand side, right hand side, so this will be P, and this should be equal to this much. So from this equation we can find the value of the P, and the value of the P will be free body diagram. We can so this will be 72 kilonewton will be the value of the force. So free body diagram will be like this. I am making the free body diagram. So this is my rod AB. I have increased the temperature, so there will be some expansion. So this is free to expand, so it will expand like this way. This will be alpha TL. So this much will it expand. Now this spring is flexible, so it will offer some kind of a flexibility. It will be treated as a some kind of yielding is promoted like this. Suppose this is my rod, it is fixed, and I have increased the temperature, so its position will be like this. So this will be alpha Tn. This force provides some kind of yielding. Suppose this yielding is delta L. So it means the final position will be here. So it will be alpha TL minus this much yielding, because this yielding is permitted already. So it will expand like this, and this spring will offer some kind of a yielding. Some means this much. So if this much yielding is permitted, so means this much amount of the expansion, this will have to be counteracted by the thermal force, because this much yielding is permitted, and that will be provided by the spring. Suppose this is 25 mm and 5 mm is the yielding because of this spring. So if this is 25 mm, this is 5 mm, so this is 25 minus 5, this 20 mm will be the length that will be utilized for creating the thermal force. So this much length, for this much length, my thermal force will be generated in this bar, so that my final deflection is 0, since both the ends are fixed. For this much 20 mm, my force will be there like this. This is my thermal force P by the spring. So its expansion will be PL upon AE. So this PL upon AE should be equal to this 25 minus 5. This 25 is alpha TL and this 5 is because of this spring. So for this much load there is 1 mm, and for force P it will be 1 upon 2500 P. So this will be the flexibility, and this should be equal to this PL upon AE, my displacement because of this thermal force. So with this we can calculate this. So this is a question. Linear elastic homogeneous uniform bar BCD, this is BCD and FG as shown in the figure, have fixed support at B and G respectively. For both the bars, axial rigidity is, this is axial rigidity means AE is 20,000 kilonewton. A gap of 2 mm exists between D and F prior to application of any load. So this is my normal positions. No load is acting here. So this is 2 mm. Exists between D and F prior to the application of any load. P is equal to 0 in this case. Now small deformation and infinitesimal strain assumptions are valid for the given bars. The magnitude of the horizontal reaction in kilonewton at B after application of the axial load of 20 kilonewton, this what will be okay. Now there are two cases. Suppose if in this case is 2 mm gap is not there, in this case my final displacement delta will be equal to delta 1 plus delta 2 plus delta 3, whatever it is, this should be 0. Since both the end are fixed, so final displacement, the summation of the displacement of the individual part, this and this will be equal to 0 in this case. But this is not the case. In this case, some amount of displacement is permissible, and how much this will be? This is 2 mm. It means my final delta 1 plus delta 2 plus delta 3, this will not be equal to 0. This will be this much, 2 mm. I can also say this is my bar, this is 2 mm. So wherever you can place. So my final delta 1 plus delta 2 plus delta 3 is equal to this much, 2 mm. This is the yielding which is permissible here. Now for finding the total the magnitude of the horizontal reaction at B. So at this end B, horizontal reaction I have to find. Now for finding this, suppose I have to draw the free body diagram of this one. Suppose there is a reaction of RB here, any direction you can assume. So if I draw the body diagram here, this will be like this. This is 20 kilonewton. Suppose this reaction will be RB, reaction at B. So this RB is the reaction here. Now let's draw the free body diagram here. You cut this portion BC just to the left of this. So for BC portion it will be like this. This is RB. So obviously this will also be RB. Now for CD portion, or you can say CF portion, whatever you can say, for CD or CF, the length is 5 meter. So for here, what will be the value of the force here? This RB is acting in this way, and this 20 kilonewton P is acting in this direction. Suppose my this reaction RB is greater than this one. Suppose this is 30. So what will be the net force here? 30 minus 20. So it will be RB minus 20. If I take this direction, this is more than this one, suppose. So this will be RB minus 20. And the same force you can apply here. So this will be RB minus 20. Now for this portion, this you forget about this 2 mm. So either you can say CD or FG, whatever you can say. So this is DG you can say. So what will be the net force here? Net force here will be, since no force is acting, so my force will be same. This is RB and this is 20. So force here will also be same. No additional force is here. So it will be RB minus 20. So this will also be RB minus 20. Means in this portion and this portion there is no change. Same force is here. You can simply write like this. So I have 3 parts, 1, 2 and 3. Now total displacement will be delta 1, this is delta 2 and this is delta 3. Delta 1 will be, what will the value of the delta 1? This is RB into its length, this is 5 mm meter upon AE. Plus RB minus 20 into length. Since force is common here, this force is common, RB minus 20, RB minus 20, so you can take the whole length, RB minus 20 into this length, 5 into 5, 10 upon AE. So this will give the total displacement. This plus this you can say, this force is same, so you can take RB minus 20 into this length, this is 5 plus 5, so it's 10. This will give the total displacement, and that total displacement of this plus this, that should be equal to 2 mm. Now this RB, this is 5 is in this is in meter, so you can multiply it by this 3 by 3. So this will give RB into 5 RB plus RB minus 20. This 10 by 3 you can take common, so it will be 2 upon 10 raised to the power 3. And this A you can, A is equal to how much? AE is equal to 20,000 kilo Newton. So this will be, you can, this is Newton. So RB you can find from here. This will be 5 RB plus 1 RB, 6 RB is equal to this much minus, this will be plus 20. And from here you can find the value of a RB. So RB, value of RB you can find from here. So it's a simple, RB will be equal to 16 kilonewton. So 16 kilonewton is the value of the RB. The magnitude of the horizontal, so RB is equal to, after calculation you will have to 16 kilonewton. The magnitude of the horizontal reaction in kilometer B at B, this after application of the axial force of 20 kilonewton at C. So this value of a reaction is 16 kilonewton. So this is the horizontal reactions at B after application of the axial load of 20 kilonewton here. So value of RB is equal to 16 kilonewton. So this is the answer. So this is 16 kilonewton. So this is the end of the lecture. I hope you enjoyed the lecture, and thank you for the listening, and good night. Thank you.